Yeah,
I was like, cool. I didn't have to memorize anything.
So you start.
I was like, cool. I just walked over and
That's good to hear.
And then you build all the PMOSs. Like from the middle.
said, yeah, take me inside. So first things first.
So you do all the
There are no
PMOSs
lab
and then you
reports.
just connect them.
There's just pre-lab and post-lab. Post-lab, you have to do during lab.
That's amazing.
Is that the order
So,
of operations?
you don't really have to worry about doing post-lab. Pre-lab stuff, they don't learn you for lecture. Because they do a lecture at the beginning, so I just do the, so what I did during the first lab, boom.
I was trying. I think he was looking to.
It's okay, it's trying to get
I was trying to come.
Look at this. And I had Reese, and then I erased it.
Oh, dude, I just made me feel better. I just forgot it's an inverter, so I didn't do one split for my brain was like, oh yeah. Because, you know, but yeah, no, and then prelims, I literally did at the first one, during it, and then I did prelim, and I just did it every time. I just do the next one. Yeah.
Do you leave your
Start
early or you
with and then to that.
Okay, give you guys some feedback on the quiz 5. It turns out quiz 5 you didn't do really well on quiz 5, and the PMOS is good at passing ones, right? And NMOS is good at passing zeros. Why is that? I'm giving credits whenever you give a close answer, but still not perfectly correct. It won't be a really simple sentence, so you just have to describe it a little bit, right? Why PMOS is good at passing ones. You can draw a diagram if you want, right? BDD. And so you turn it on, you have to give a 0 to it, no doubt on that, right? So whenever this reaches to 0, if you have a BDD here as well, it's just the CMOS will keep on. Nothing can shut it off, so it's able to pass BDD easily. But if you want to try to pass 0 to it, it's getting turned off. The VSG here is 0, right? It's lower than VTHP. Okay, that's why it's not good for passing zeros. So what's the smallest voltage it is able to pass, though? No, VTHP actually. In our case, it's about 0.9 volts. Whenever this voltage keep rising, right, keep rising to VTHP, and you got a VSG which is VTHP minus 0, which is actually VTHP. It's exactly the threshold voltage. And whenever it's keep going up, all the voltages above this voltage will be passed to here, because this is on. So for NMOS, you give a 1 here, trying to pass a 0, no problem, because because it's symmetrical, there's no difference. And 1, 0, this VGS is always 1, so it's on. So definitely you can pass a 0 to the other side, no problem, without any problems. So whenever this voltage keep going up to what? VDD minus VTHN, it's getting shut off, because this is VDD. Okay, so any voltages higher than this one won't be able to be passed through the channel to the other side of the transistor, so it won't be passed. So that's for the operation of the NMOS and PMOSes. And when you draw inverter, that was a surprise, and you still couldn't draw the schematic of this guy. Right? I saw PMOS at the bottom, NMOS on the top, and I saw different terminals. And you're creating like 2 terminals for the transistor. And even drew a symbol here. And not just one. If you're seeing like you are putting this on the quiz, you're not one of them. Like 30% of people do the same thing. So don't feel bad. And the inverter just have one terminal, right? It's one in, one out. So it's basically you need to short these 2 terminals into one. Alright? Anything else I saw here? Oh, so this happens a lot because this is relatively still new to you guys, and I mean this year I saw this one more time, but in the past I saw this a lot as well. But I was trying to give more examples in the class before the quiz, but still I see people just do this, It doesn't make sense, right? You have to control the gate in order to give it output. Alright, so these are the mistakes I saw on the quiz, and try to avoid this in the future. Any questions on this? Just very quick feedback from the quiz. So this is not really a big deal, I think. It's relatively simple. And we're going to have a quiz on stick diagrams and AOI logic circuits, but really simple one. Give you 15 minutes to work on it. So before that, we'll cover a lot of examples to make sure you guys are prepared for the quiz. Remember last time we talked about parallel transistors, right? If we have 2, the stick diagram looks like this. Wait, the PMOSes are crosses. So 1, 2, 3, diffusion, gates. We have 2 options. Okay. Three. Remember? This. Method 2. Same. Four. You need the 5 notes. 4 fingers. Let's see if this is the case. You got one terminal from the VD dumping current into here. So this one goes this direction, this one goes there, and merge here, right? And this goes here, and merge here, and eventually merge to one channel. So it's going to be a 4 in parallel. That's how you draw it. Any questions on this? Another way to do that: 1, 2, 3, 4, 5. Okay. Five. So for 5, you need the 6 nodes. Five fingers. I'll give you several seconds or 1 minute probably to see if you guys can get it. All right, if you get it, let me know. I can let you come here and draw on the board if you want, but you don't have to. See if anyone can figure this out in a minute, 2 minutes or so. It seems like the odd number of transistors are always in the same pattern or similar pattern, and even numbers are in another similar pattern. Done? You wanna- Yeah? There should be a lot. It's a classroom. Yeah, 一下就要去装的。Yay. Cool. Thank you. Good job. All right. Questions on this? Let's see, that's the case, right? So we'll have this, 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 this. So totally 5 branches. 1, 2, 3, 4, 5, and they all merge into this single node. Okay, like this. Cool. Right, now let's take a look at more examples over here. What about A, B, C, or D, E, F? Bar. So design the schematic first and then convert it to diagrams. So schematic first. 6 transistors. Because six signal lines, right? So 6 transistors. And always think about the NAND gate and NOR gates. So this is a NAND gate structure, so the AND logic, and then the 2 entities got OR and then bar. So the AND logic, think about the NAND gate. The NAND gate has big hat and chicken legs. So the big hat has parallel PMOSes and series NMOSes. Okay, so get that sorted out first. And then they are getting ORed, so which means think about the NOR gate. It's actually these 2 parts, big boxes are in series. So it becomes 3 parallel transistors, and then in series with another 3 parallel transistors. Okay, so these are A, B, C, D, E, F. So for these 2, think about the NOR gates. Remember, the NOR gates have the 2 entities, the 2 boxes in parallel at the bottom. So NOR gates have big legs and small head. And these are in series. So you have A, B, C, D, E, F. Okay, now let's convert it to a C diagram. Any questions on this before we move forward? So just keep using the same pattern, the same tradition we have been using, and without thinking about why, because we already explained it a few lectures before. So let's just keep using this conclusion, right? So just follow this pattern. You can see how I designed, how I converted from here to here, and it works fine. And then let's use the same method we've been using to convert this one to the stick diagrams. So 6 transistors. So draw the top rail first, the VDD. 6 transistors requires 7 nodes. One liner. So 3 in parallel first, and then the other 3 in parallel. Based on the conclusion here, we know how this transistors 3 in parallel looks like. It's either this or this. So which one would you like to use? And why? Huh? The bottom one? Huh? You got a VDD here, ground here. So that's the output. Output comes from this node, and I couldn't go because I have another 6 over here. Oh, another 3 here. The top one, because you got a VDD here, and this one is directly making a contact with the following 3. So this is better, okay? For that case. So how do you want to do it? Introduce VDD here and do this. And then what? I mean, you already know how to do it, right? So you introduce the one node from VDD, you can do it here with the 3 in parallel. Why not here? It's still same node, just one node. Just don't use VDD, but use this one as one node, and then make a parallel. How? This, right? Okay. Unknowns. This is easy. Just 2. It's basically 2 in parallel. So you use these conclusions. 2 in parallel. This one, right? 2 in parallel. It's just that you have more transistors in the middle. Instead of 1, you have like 3, but still just 2 branches. For the one-liner circuit, this is easy. So just 2 branches. You introduce, this is the output, right? This is the output. Just 2 branches. Okay, got split. 2 branches. So these are in series. You don't need any fancy wires in the middle. So these are in series, 2 in series, and the order rows, these are in parallel. So now another thing is we have to consider the labels, because we want to get rid of all these crossing of the poly, the gates. Implement it into the layout. It's a physical design. It's not something on the paper. So what are the A, B, C's, and D, E, F? What are these? Which one should be labeled as that? So you want to start from here probably, because this one, you can see the labels is from A to C with a certain order, and the B is in the middle, A is on the top, C at the bottom, directly short of the ground. So this has to be C actually, right? So CBA, like that. Or it's ABC. You cannot change it. It's DEF. You won't be able to change it. If you change it, it won't pass the LVS or NCC. So in that case, does the order really matter for the PMOSes on the top?
They just have to match the.
Yeah, so these 3 doesn't matter, right? These 3 doesn't matter, but you have to keep DF. So DF has to be here, right? So ABCs has to be here, but within this, doesn't matter. The order doesn't matter because they are all symmetrical. So in that case, I can actually just directly label, just match it, and there won't be any problems. These are interchangeable, so why not just name this A, B, C like that instead of BAC? Well, still fine, but you're getting a crossing poly. Same for the right hand side, right? So just DEF to make sure there's no crossing. And then when you are laying on the poly, it's just easy and happy connections. Left click and right click and give you a little sound. Super satisfying. Done. Okay? And then when you are trying to, so these are polys, definitely for metal 1. This is the output, no problem. And these ones are, you have to do that little connector, right? One by one. And introduce metal 1 to the left. That's how that works. So another thing you need to know is, for the design, I told you guys, but I want to stress this one more time. So we put all the, so these are, for our design, you know, we are doing all these, what are these called, remember?
It's just power.
Yeah, VDD. Untaps, right? These are untaps. I think in electro VLSI, they are called unwell. Probably unwell. So unwells are being put in here, and you know the PMOSes are like the PMOSes. Every time you put a PMOS, the PMOS has an unwell with it, right? Okay. So you can imagine the unwells are pretty much some unwells here because these are unwell tabs. You have unwell has a tab on the top. So eventually you can imagine on the, because this is the top view of the wafer, I can imagine the unwells are in the irregular shape, irregular shape. Because here is one unwell, there might be some overlaps. These are unwell. That's not good. Even though there's a contact, but unwell will be in a really weird shape. So what we usually do is we keep all the PMOS in the same unwell because they are in the same unwell anyway. So you drew a pure unwell here as a box on the top to just make sure the overlap. So to cover all the PMOS and untaps. It doesn't matter. I mean, you can say, hey, you got 2 layers of unwells. Does that matter? You got 2 layers of unwells. Is that the case? No. Because they are unwell is the same layer. You are not getting 2 layers. So you get a 1 layer on the top of the other layer, but they are the same layer. You are not getting 2 layers. Whenever the TSMC or Global Foundry they are fabricating a chip, they see this whole thing as one unwell layer. They'll just put one unwell on it. There won't be like multiple unwell depositions. It's just one unwell. Okay, just keep that in mind. Because eventually this turns out to be just the one unwell. Okay, so for this guy, I think in electro VLSI, they treat the P substrate, the wafer itself, the body, as a P well. I forgot if we have to do a P well cover as well, but I think just let's assume it is that way. So we do that as well, and definitely unwell and P wells, there shouldn't be any overlap. Okay. So you need a gap. So there's a certain DRC rule to define the gap, so it cannot be too close to each other. So which means the same thing as because NMOS all the NMOS actually have the P well with it, right? The P well, the dots. I think the slashes. So these are dots. If you move the slashes too close to the dots, and there will be a DRC error reported. Anyway, so when you use a big slash area like a P well and big dots area like this, you want to also keep a certain distance. So what about this? I have the slashes of this NMOS. It's like this big. Okay. Would that matter? Does that matter? So the goal of drawing this box is to cover all the P wells.
Yeah.
Why do we have to leave a little bit over here? Just cover it. Just look at the boundary of all the P wells and just cover it. That's the goal. Okay, just do it.
Is it manufacturing error?
Yes, it's good for manufacturing, and also just keep in mind. For example, you for the unwell. For example, an unwell. If you got a PMOS which is this big, and when you draw the unwell, it doesn't cover this part. You can see this corner probably won't be able to be resolved. It's reporting DRC errors. That's that little piece. It's too sharp, too small. It's the feature, the size of the feature is too small, so the foundry cannot resolve it. You are getting DRC errors sometimes. So just cover the whole thing. Okay, just cover the whole thing. Okay, question on this? Cool. Let's cover more examples. I'll give you more examples. It'll be good for the homework. This one. This. Do you have a universal bar on the top?
No.
No. So we want to convert it. De Morgan's law at 2 bars on the top. So this guy, two bars get canceled, just 1 bar left. I can remove the parentheses too if you want. It's basically just a 4 input NOR gate. Just a 4 input NOR gate. Any questions on this by far? 4 input NOR gate. Treat this one as 1 signal, okay? And then you start drawing that schematic, the AOI logic. Okay, so that's the AOI logic schematic. So what about the stick diagram? I'll let you guys work on it for a minute. I'll see if anyone can come over and draw on the board so we can discuss. This one's not that bad, right? Just 4. I'll just do it with you guys. 4 e to the 5. Okay. So 4 in series is pretty simple. In series, how to deal with that? Just this, right? In parallel, 4. Look at your notes. Which is better? You have two different ways to do it. Which way is better?
2 inputs.
Parallel, 4 in parallel.
2 inputs, 3 outputs.
2 inputs, 3 outputs. Like this. So it's basically comparing this to this, right? So the 4. We picked up this one instead of this one. And is there a rationale on that? Why this might be a little bit better? I agree with that actually.
There's less in between. There's less comma.
Less wires in between, less wire here, so you have more room to route filters. Good. I like that. give you yourself more space in the middle to route. All right. What about the gates? A, B, C, D not, right? These are signal lines. And you don't have a choice because that has to follow this order here. And these are in parallel, so the order doesn't matter. So why not just directly align with the one on the top? Okay, so you can directly draw the polylines. Any questions? No. But the quiz will be too simple for you guys if you guys can handle all these kind of reasons. I'm gonna change the quiz right now. So this looks similar, but it's actually a little bit different. It's basically two blocks, right? Two blocks, and think about the NOR gates. These on the top of the for the PMOS has to be in series. So you're expecting a long chain on the left and one on the right, and in parallel with it. Like this. And for the NMOSes, the two big boxes are in series, because of NAND-gate structure, right? And then you have three in parallel, right? So then you have two different choices. Would you like to put this single one on the top or the parallel one on the bottom, or vice versa? Which one? We can try both. Three first. Let's do that. It doesn't matter, okay? So you can put this on the top or put this at the bottom. Doesn't matter, okay? So for this one, let's design the SIG diagram and see if this is easy or not. So we got 4, so you need 5 nodes. Just 2 branches, easy. So 3 in series and 1 on the other side. You could just do this. Okay, so it's gonna run through the 3 and run through this guy. Agree with that? What about the bottom one? So the output comes from the top, and you have to deal with 3 in parallel first, and then 1 in series. So in this case, I think we should think about the labels of the fingers first. So for this case, there's no choice for this guy. It has to be D. And this is following a certain order from VDD, and you can see A is shorted to VDD directly. So that has to be A, B, C, like this. In that case, for the bottom one, we really want to make this to be A. Can we do that? So we really want to make A, B, C, and D as well. So they're not crossing. Is that doable? So remember the 3 in parallel structure, right? 3 in parallel structure. Out of the notes, you can figure out the 3 in parallel structure. So if they're in parallel, the order doesn't matter, and we could just introduce it here and do this. So that's a 3 in parallel structure. Wait, that wouldn't work because these outputs is not directly shorted to ground, so that doesn't work actually. What are the options?
Well, we know D's directly shorted to ground in the series.
Hmm?
Let's start there.
Because D is at the bottom like a tail here.
Yeah.
So you are creating an output of the parallel transistor. So the output has to interface with one single transistor. So in that case, if you want to make this side to be D, you want to make this, because this is D here, right? You want to make this to be D as well. This joint has to be the output. Shouldn't directly take the input from the output on the top. So we shouldn't do it here, right?
Yeah.
What is the other option though? You use this node as the output. So make the three parallel transistor here and eventually output here, right? Output here, not as the beginning. So if you do this,
Yeah.
and this becomes the output of the parallel transistor. And the order of the parallel transistor doesn't really matter, so we can label them as A, B, C without any problem. So in this case, they're all aligned, no crossing. Right? So what about the other option? If we flip it or swap it to the top. So D first. Doesn't matter, right? So D can come first or come to the last. It doesn't matter. It's the same circuit. No, same logic. That's going to affect your stick diagram. Not the PMOSes, though. The PMOS is going to stay the same. Still doing this.
So you have 2 connections from ground
Uh-huh.
on the left side. So it'd be the far left and the third from the left.
We still keep this in mind, okay? Keep this in mind. All right. So which one you want to engage first?
C.
Huh?
It'd be the transistor C.
C. Why?
Just because it's on the edge.
You mean this guy? Or this guy?
Oh, the NMOS.
NMOS. Okay, this guy. It's just one of the parallel transistors. And they have to, the output has to go to ground. But between that, the output from the top goes through one transistor first and then do the parallel thing. So you actually want to engage D first. So here's the output, right? Which one should be D? I mean, we hope this is D, right? We hope this is D. Can we make this into D?
Yeah.
Yes. So where's the input? Here?
Yeah.
Here? Which one?
That one.
Okay. Yeah. Right? Just one current stream. Done. Rich is here. Rich is here. Then what? Do a parallel, right? Just do a parallel. No.
Oh, it's actually simple.
And the order here doesn't, yeah, this is actually simpler. So the order here doesn't matter, so we can directly assign A, B, C without any problems. So the experience learned from this example is that if you have things like this in the future, it's probably easier for the layout if you put a single transistor on the top. instead of the bottom. Even though this example works, but maybe if you got a more complicated ones, it could be a challenge. So we got 1 here. What about 2? You got 2 in here in parallel. Then do this. Would you like to look into that? It's probably useful. Let's take a look. So what about this? Sorry, osmosis. Let's just deal with the unknowns at the bottom, okay? Just this. So here's the signal output from the top, right? Just ignore this. You got a signal here. 2 in parallel and then 3 in parallel. 2 in parallel first. Not too bad, right? How to deal with the 2 in parallel? Which option would you like to choose? Which option? Which one? This one? Then you got a 1 output from the middle. You won't be able to. This one, right? Yeah. This. So here's the output. Then you can do the 3 in parallel thing. Okay? And I believe it wouldn't be a big problem if you want to align to the PMOSes, and I don't think that's going to be an issue. But any questions on this by far? No? Let's look at another example. If we don't simplify it, so this is parallel for PMOSes, okay? PMOSes, parallel, 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 and then in series. For the bottom is easier. How to deal with that? 2 parallel first, output to another 2 in parallel, another 2 in parallel. Can we just use a regular method, the one we have learned, to deal with that? See? Like you are thinking, hey, which one we should choose? Definitely this guy, because if you do this guy, the output is in the middle, it won't be able to connect to anywhere. Have to be this one, right? Right? Okay, let's do it. Now I'm gonna do A and C. I don't have other choices. How to do this? One in the middle. Bad. I have to choose a different way. I have to go through a different route. This wouldn't work. there a better way to do it?
I guess you'd have to, let's say you have to do 2 prongs.
Hmm?
So you'd have to do
Yeah, see, every year we'll have 1 or 2 students in the class are super good at this. They are not naturally at other things, good at other things, but they are super good at this. Like last year, I had one student in the class that came up with a super genius idea about this circuit. Think about it.
So you do like two prongs and a 3-prong on the bottom.
Like try it here. Doesn't matter if it doesn't work.
Oh, I don't
Have a marker? You have a marker?
No.
No. Oh, wait. Zach. Thank you, Zach. Yeah.
Thank you, sir. I don't know if that'll actually work.
But do you need a connection to this guy? Because this is gonna short all the things. It's very close though. So you are the one. You are pretty much the one.
I don't know. if
Think
I'm
it,
the
keep
one.
thinking about it. I mean, it was very close.
Well, because you have to connect A and B.
That's right.
And the other 2.
Okay, then start from here. Think about this. What else we can do?
Well, yeah, so
If
that-
you do all these, but all these will make everything parallel, right? We probably don't want this. Right? It's just 2 in parallel. It's just 2 in parallel.
No, no. Oh yeah, that's right. So then.
So 2 in parallel, then we need another 2 in parallel after that.
Yeah, so I guess that would have to be these 2 because they're in series with these. So it would have to be. This.
Yeah, that's another. Yeah, but
And
the.
then that shorts the.
What about these 2? No, these are not. This is fine. What about these 2?
I guess could you do this?
Yeah.
And
And then what?
that would be your.
Mhm.
No, because you still need.
It's
this.
getting super close. Just one more wire, you're done.
But if you connect this, wouldn't this short all of them together?
Do you have options? Just flip it to the top.
Oh yeah, that's true. This.
No, flip the bottom one to the top.
This bottom one's at the top.
Here.
Oh, flip the 2 connections. You have. Okay, I see what you're.
This, right?
Yeah, so you flip.
No,
this.
keep that one. Right.
So like this.
Yes. And then what?
This. Is your elbow?
Done. Yeah.
That's. Oh, that's really.
Take a look at it and think about it.
That feels illegal.
Let me know if that works.
That feels illegal.
Let's do a 201 for the quiz.
That feels wrong. Well, one and
Good job.
actually do.
Good work.
So, yes. Yes. There's so many patterns you can get.
It's true.